This is where we ended. I thank Or for noting that this should be n and not n minus 1, but it doesn't matter in the lower bound. I wanted to show you the proof of the theorem, which I will not get into, but the proof is not difficult. There is only one keyword that I have to use, okay? So talking about lower bound techniques in proof complexity. So the keyword is random restriction, okay? This is a technique which is used constantly in proof complexity. So that's one thing you use in the proof. But the idea is basically that if you have you want to show that if you have a short proof, then you can transform it into a proof which is narrow, which doesn't contain any wide clauses. So the problematic thing that can happen that you have a short proof, but there are quite big clauses in it. But clause is a disjunction of variables. Now, what will happen if you pick a variable at random and you fix it to either 0 and 1 or 1? So if you have a big clause, that with a pretty decent probability, you will pick a variable from that clause. If now the variable appears positively in the clause and you fix it to 1, then the whole clause becomes true and it's completely useless in the proof. Like a true clause which is evaluated to constant 1 cannot be used in a refutation, so it disappears. And that's basically the idea and a little bit of computations. But random restriction, that's the keyword. And maybe I shouldn't have called this lower bound for resolution, but lower bounds from random restrictions. Oh yes, but I need to use the keyword. So now...
You have to worry that it's still unsatisfiable?
Yes. Okay, you have to do a little bit more. So, of course, what you want to do, like after a restriction, of course, it stays unsatisfiable, because if you restrict something unsatisfiable, it stays unsatisfiable. What you should worry about more, what happens to the original clauses, because the restriction kills some clauses in the proof, but it will also be killing the clauses in that you have started with. But the clauses you have started with are small, and you massage it a little bit, and you have to apply the restriction, and then using the restriction, recover a refutation of the original set of clauses, not of the restricted clauses. So now I will move to a different, let's say, proof technique, and that is by reduction of proof complexity lower bounds to communication complexity. So communication complexity Anup will be talking about, but so if what I say doesn't make 100% sense now, it will make more sense after Anup is talking. But communication complexity is a big field which talks about complexity of communication. And now, in this approach, I would like to reduce lower bounds on, let's say, resolution or some other proof system to known lower bounds from communication complexity. And the general strategy is as follows. So you will have a CNF, and you partition the variables of the CNF into two disjoint sets. And you consider the following communication game. So Alice has a truth assignment to the variables x0. Those are the variables LCs. Bob has an assignment to the rest of the variables. And since the whole CNF is unsatisfiable, there must exist a clause which is false under this assignment. And the objective of the game is to find such a clause. So you think of it as the original set of clauses. So every clause is just a disjunction of variables, which means that you can write a clause uniquely as C0 or C1, where this is the part of the clause which depends on the variables x0, and this is the part of the variables x1. Alice completely knows this value of the clause. Bob knows completely this value of the clause. And they are supposed to find a clause which is false. Or put yet differently, so the clauses look the following way. So Alice knows all of these, all of the C0s, and Bob knows all of the C1s, and they are supposed to find a clause which is false, which is basically the intersection between the false clauses that Alice sees and the false clauses that Bob sees. And that's the communication game. Now, I would like to make a very simple observation that if you have a tree-like resolution refutation of C of size S, S is the number of inferences, then the deterministic communication complexity is at most log S. Meaning that Alice and Bob can solve this game by exchanging at most log S bits. Or in other words, if you manage to prove a lower bound on the communication complexity of the game, you get a lower bound on the size of the proof. I emphasize that we are talking about tree-like proofs here, and this will be so in all of this discussion. And the proof is simple. So here we have your resolution proof, which is tree-like. Those are the original clauses. And it has S inferences. And the proof is known to both of the players. Okay, the proof exists. Both of the players know what it is, and they use this proof to construct a protocol. So this thing is a tree, which means that somewhere in the tree there will be a node such that the size of this thing is roughly the half of the size of the whole tree. Meaning that the size of this is somewhere between S over 3 and 2S. So this thing is not too big and not too small, which means that the complement here is also not too big and not too small. So now what the players do is that they look at the clause C sitting here, and they exchange one bit by or to agree what is the truth value of the clause under the assignment. So remember that what they have is an assignment alpha and beta, and the clause C is just a union of something such that Alice knows the value of this under her assignment and Bob knows the value of that under her assignment. So they can evaluate this by just exchanging one bit of communication. And that tells them what is the value of this clause. Now, supposing the clause is false, so it's false, so they know that if they look at this subrefutation, the subrefutation will at this point get to this false clause. So they look at this tree and they continue in the same fashion. If this clause is true, they just remove the tree, this subtree, from the proof, and they zoom in on the rest of the proof and continue in the same fashion. Until at some point they must reach one of the initial clauses and the initial clause will be false. And that's the proof. So at every step they exchanged one bit, and they, in roughly log S steps, they identified an original clause which was false. Maybe one detail about this proof. It's quite tempting to prove this thing in a different way, that you would start from the empty clause. The two players know that this empty clause is false, and now you know that you have used it to resolve X and not X. Now, depending on which player knows X, whether X is known by Alice or Bob, they would decide whether the predecessor is false, and they would move forward upwards in the tree until they reach a clause. That's a way how also to prove it, but it doesn't give the right answer, because then you would bound the communication complexity by the depth of the tree and not by the size of the tree. And it can happen that the tree may be very deep and small.
But then can't you balance the resulting communication protocol?
Yeah.
Yes, okay, you could do that. So, yes, so that's exactly this argument. So, of course, you could, from the protocol, from the proof, you could get a tree-like protocol which is small, and then you could balance the protocol. Or you can directly do this. So, a nice application, which I will not give a proof at this point, is the bit pigeonhole principle. Again, so now remember that the bit pigeonhole principle said that there is a 2n plus 1 by 2n matrix, such that all the rows of the matrix are distinct.
And
now, if you think about the communication game, you have to define how to partition the variables. So there is one natural way how to partition the variables, and that is partition it in this way, meaning that Alice would know this part of the matrix, and the Bob would know the other part of the matrix. Which basically means that for every pigeon, Alice knows. So you split the pigeons. You split the pigeons into halves, and Alice knows exactly where her pigeon goes, and Bob knows exactly where his pigeon goes. And you are supposed to find a collision between the pigeons. But it's a relatively easy exercise that if you do it this way, the communication game will actually have small communication complexity. So this is not a right partition. The partition that works in this case is that you partition the variables like this. So you partition the bits of the wholes into two parts. So no single player has any information about where each pigeon goes. He knows only half of the bits of each pigeon. And in this case, one can prove that if you partition the variables in this way, the resulting communication game will require something like square root of n bits, which then gives you 2 to the square root of n lower bound for the bit pigeonhole principle. Now, I'm not going to prove the lower bound on the communication game. It's just an illustration how you can apply this strategy to prove a lower bound. One thing to note, of course, is that the lower bound we get here is weaker than from the width-size trade-off. And also, again, it works only for tree-like proofs. So it's weaker in both the parameters and what it's actually proving, and the proof system that it is actually working with. There is a different application, and matching communication upper bound might be. I don't know, because if the upper bound I stated is the correct one, then actually the trivial protocol would. I don't know. It's unlikely, unless it's the trivial protocol. Here's a different example which I will use later, and that's a little bit more well known, and that's the Clique versus coloring. And so let's have n squared vertices, or n choose 2 vertices, which you think of as representing a graph on, let's have n squared variables that you think of as representing a graph on n vertices. Now, introduce one formula which says that you add extra variables and you say that the variables represent a clique of size k plus 1 in this graph. You can write this as a CNF of a small size by, let's say, saying that here is your graph G, which is on n vertices, and your additional variables y would say that there is an injection from a set of size k to some subset of G, such that everything in this subset is connected. And you can write this as a CNF of a small size. Okay? Another thing is that you can also express the fact that Z is a k coloring of your graph in a similar way. So we'll have another formula which says that the graph G is k colorable, which would be a similar way how to write it. I hope it's clear that how to write such a thing, but hopefully it doesn't matter very much, okay? The specific way how I express the clique and coloring CNFs is not very important. There is one little detail that I'll mention later, but the only thing that is enough how to write it to know that having a clique is an NP property and a coloring is also an NP property, hence you can write it as a small CNF. And you can write it as a nice CNF if you want in this way. Then the observation is that this CNF is unsatisfiable. Okay, so it's impossible to have a graph which has k plus 1 clique, which is at the same time k colorable. So this is an unsatisfiable CNF. And I would like to show, again, using the same argument, that this particular CNF requires a large resolution refutation. And the previous game sort of looks a lot like the following game. And that's a Kaczmar-Wigderson style game which looks as follows. You have two players. Alice has a graph which has a k plus 1 clique, and Bob has a graph which is k colorable, which means that there exists an edge in the graph that Alice has in G, which is not contained in the graph H. Okay? Because otherwise G would be a subset of H, which is impossible. So if you have any graph G, which is a k plus 1 clique, and a graph H, which is k colorable, there must be an edge in this graph, which is not in this graph. And now the objective of this game is to find an edge which is in G and which is not in H. Unfortunately, if you choose the parameter k in a suitable way, think roughly like square root of n, then the communication complexity of this game will be n to some constant, which follows from like lower bounds of Rasborov on monotone circuits, or Ras-Wigderson, which gives explicitly lower bounds for this game with a little bit better parameters. And now this sort of implies that the clique versus coloring requires tree-like resolution refutation of like exponential size. Well, this is a little bit cheating, because if you remember the clique versus coloring, I don't really know how to partition the variables in an intelligent way so that you can directly apply this argument. But there is a little trick, and the trick will be useful later. So here we have the CNF, which is the clique. Coloring. And now I would like to partition the variables into two parts in such a way that the resulting communication game will boil down to this Kaczmarek-Wilson style game, so that I can apply the theorem of Rasborov and others. But as far as I see, this is not possible. So instead, one modifies it in the following way. So for every variable x, you introduce a copy of the variable, and you will consider the following CNF. So you will have a variables x, some other variables x bar, and then you will introduce a condition which says that x is at most x bar. By which I mean you introduce all clauses which says that not xij or x bar ij. Okay. Now, this original thing was unsatisfiable. This is also unsatisfiable, because this is now saying something slightly different. The original formulation says that there is one single graph which contains a clique and is at the same time colorable. Now I'm saying something slightly different. I'm saying there is a graph which is a clique, which is contained in a graph, which is k-colorable, which is contained in a graph which is k-colorable. That's also unsatisfiable. That's one thing. Another thing is that actually the original formulation can be obtained from this formulation by resolving the additional variables. So one thing I haven't told you about the clique, which is important, that in the way how we formulate the clique CNF, all the variables x are actually monotone. There is no negation in front of the variables x, which is reasonable to expect, because if a graph has a clique, then every big graph also has a clique. But now, since all of those variables occur positively, I can resolve them with the variables that occur here and actually obtain the original thing I started with. And now I hope it will not shock you if I do it the other way around. Just do it. So I can obtain the original thing by a short resolution proof. Which means that if I manage to prove a lower bound on this, then I'm also proving a lower bound on that, on the original formulation. Okay? And now look at this CNF. So I'm claiming that the communication game, if Alice knows the variables x bar y, and Bobs knows the variables xz, is at least as hard as the Kaczmarek-Wilson game over there. Why is it so? So suppose that Alice has a graph with k plus 1 clique. So this is the graph. It has a k plus 1 clique, so she fixes the assignment y so that this CNF is actually true. Okay? Similarly for Bob, he has a graph which is k-colorable. That's the graph x. He fixes z to be actually the coloring of the graph, which makes this CNF true. And now they are supposed to agree on a clause in here which is false. But it cannot be a clause which is contained here, so it must be a clause which is contained somewhere here. That is, in other words, they found some clause of this form which is false, which means exactly that they have found an edge which is contained in G and not contained in H. So this gives a so this shows that the complexity of this game is at least n to some epsilon. Thanks to that theorem from elsewhere, we know that this is n to epsilon, and we have a lower bound on resolution. So far, this was just a different way how to prove lower bounds for tree-like resolution, which we already know. But coming back to the original theorem, there is very little actually about the resolution proof system, which we actually used. Okay, in the argument, we used only the fact that in every line of the proof, Alice and Bob can decide cheaply what is the truth value of that given line. So as long as you have a proof system with this feature, that every line in the proof can be cheaply agreed on between Alice and Bob in this communication game, then you automatically get a lower bound. So one illustration is cutting planes again, okay? So now remember that the cutting planes were just linear inequalities. The lines were just linear inequalities. Now, if you split the variables into two parts, the left-hand side also splits into two parts. And Alice or Bob knows exactly the value of his half of the linear function. Unfortunately, Alice and Bob cannot tell each other the value of the function that they see because it's some integer. We didn't impose any bounds on what the integer might be, so they can't really transmit the integer. But let's say if I restrict myself to cutting planes where the coefficients are small, so small, then the amount of communication they need to agree on the value of the clause will also be small. And you get a lower bound for cutting planes, tree-like cutting planes with small coefficients. Okay? By exactly the same argument, and you don't have to think about it. In general, if you don't want to restrict the coefficients to be small, then instead you would use randomized protocols. And one can show that you can use small randomized protocol for the two players to agree whether the inequality holds or not. And then the rest of the argument becomes the same. And this, I think, is again the result of Russell.
With Tony and Alistair.
Thank you. This also kind of shows one nice thing about this generic approach, is that to get this lower bound on cutting planes, you actually don't need to know anything about cutting planes. If you remember, there were three rules. Some of them was like multiplication by a constant, adding, rounding. So in this approach, it doesn't matter at all what rules you used. The only thing used were the properties of the lines. And if you decide to use some more complicated rules, the lower bound still holds. The only thing which matters in this argument is what's the communication complexity of each individual line in the proof, not the complexity of the rule itself.
Just the theorem that you stated about the Kazma-Wigderson game, that is true also for randomized?
Oh, Yeah. Oh, okay. Yes, that's a very good point. Sorry. Yes. Okay, that's a very good point. So, then of course, I have changed the protocol into randomized, and I need a lower bound on randomized protocols. So, the lower bound of Rasborov and Alon and Bopana is for deterministic, and it's actually a stronger lower bound which works for monotone circuit. But the lower bound for Raz and Wigderson is actually for randomized protocols. So fortunately, in this case, you have a lower bound on randomized protocols. There's a different application, and which I find very nice, and it's an exponential lower bound for tree-like degree D cutting planes, where you again strengthen the communication models. So in the cutting planes case, one strengthened the communication model to be moved from deterministic to randomized, but here one also allows like multi-party communication. The degree D cutting planes I will not exactly define, but you can think of it as cutting planes where instead the inequalities are degree D polynomials. Okay, so let's have the case that D is equal to 2. So your lines would be any expressions of this kind. So those would be your lines, and then you would have some rules telling you what to do with those lines and how to combine them. Now, the point is that if you split the variables into two parts, then the players no longer can determine whether this inequality is valid or not. Because in this case, every monomial was observed by at least one of the two players. Whereas here, there will be some monomials which depend both on x0 and on x1, so the two players cannot agree on the value of the inequality. But if you now split the variables into three parts and use the number on the forehead model, then the players can actually agree on the value of this inequality plus some randomization. So in the degree 2 cutting plane system, you would use multi-party communication. That's just to agree on this clause. And then there is this randomization, which is again just to handle the values of the coefficients. But let's say if we were modest and just wanted to prove lower bounds for systems where the coefficients are small, it would be enough to take a deterministic number on the forehead protocols. And the paper of Beam, Paul, and others, it reduces the lower bounds on this sort of system on multi-party communication complexity of disjointness. Now, one thing that I like about this paper is that I'm not 100% sure what the history was, but the paper reduced the lower bounds in proof complexity to communication lower bounds before the communication lower bounds were actually known, which that's true, which sort of justifies many of our papers, because you often reduce some problem you cannot solve to apparently even harder problem that you cannot solve, and it seems useless. But here they reduced a problem to a problem that actually later has been solved, which is nice.
And here the randomization is again needed because the coefficients are not bounded.
Yes. So if you work just with bounded coefficients, then you don't need. Sorry. Well, there are several things. Okay, so one of them is to make this proposition true. Okay, so I want to have a connection between size of a proof and communication complexity. So if the coefficients are bounded, then I don't need randomization. I just need three parties, let's say. That's one thing. Another thing is how to actually prove this result, how to prove the reduction from to the communication complexity of disjointness, okay? That's another thing, and that also uses randomization for different reasons, okay? So the randomization here is, so even if the coefficients are small, to prove the lower bound in this way, you still need to randomize it. So this is so this is how to prove lower bounds on tree-like proofs. It's quite a general technique which works sometimes, sometimes it doesn't work. But it seems that it essentially works only for tree-like proofs. So it seems that this cannot be extended in a reasonable way to proofs which are non-tree-like. And those two examples that I gave are just, there are several other examples where you can actually prove lower bounds in proof complexity using this way, which we don't know how to prove in any other way. There's a bunch of other examples.
In the randomized thing, there is a log n or log something?
Well, let's see that. So it's tree-like degree decutting planes. So let's stay on the safe side and say that D is fixed. Or did I miss the question?
Maybe.
So let's say if D is fixed, like 1,000.
For the first one, for the cutting plane, because to do greater than you need some error.
Yes, yes.
You need some log n. You need
There is some log n or log n, which I don't remember.
I think epsilon log n.
There is some loss. So now I will talk about something which looks different but is closely related, and it's called feasible interpolation, which I think of basically as what we just saw about communication complexity, but sort of jazzed up so that you can actually apply it to non-tree-like proofs, to general proofs, to proofs which are not just trees. And I'm not sure how apparent the connection will be, but let's let's see what's going on. So feasible interpolation, the general setup is the following. So you again prove a lower bound, and before we were trying to reduce it, the lower bound to a lower bound in communication complexity. Now I want to reduce it to a lower bound in circuit complexity. So you have a proof system and a proof of some tautology, and you will show that if there is a proof in your proof system, then you can solve some related computational task relatively cheaply, and then prove lower bound in computational complexity to get a proof complexity lower bound. And the way how people usually make it work is the following. So in the communication game we had before, there were two sets of variables and two players. Here, for some reason, there will be three sets of variables, x, y, and z, and you will have an unsatisfiable formula of the form ax, y, and bx, z, meaning that the formulas a and b share only the variables x, and they don't share the variables y or z, which is actually the situation we already discussed, like in the clique and coloring. So we had a clique which says that the graph represented by x has a clique, and coloring which says that the graph represented by x has a
What was the role of the y there?
The role of the y? Well, the role of the y was mainly to shrink the formula, okay? So I cannot say, if I want to say that the graph has a clique as a CNF, I cannot do that so that the CNF is short. Okay? I can't even do that by an arbitrary formula unless something very strange happens. So the role of the y is to just shrink the formula and to have something which expresses that the graph has a clique, but expresses it in a succinct way. So the size of this formula is polynomial in the size of the graph. If I didn't have the y, then it would be exponential. So that's the role of the y, and similar, the role of z is also just to shrink the formula.
So it could be something along the lines of y is a clique in X and has size k plus 1.
What?
So y might give you the clique.
Yes, y gives you the clique. Think of y as actually being the clique, okay? This says that y is a clique in the graph X, and this says that z is a coloring of the graph X, okay? So it just gives you the witness. Now, if A and B is unsatisfiable, then there exists a C such that the following holds. So A implies C and B implies not C. Okay? This is obvious because if you just having A and B as unsatisfiable CNFs, if you look at the set A, which is the set of all x's for which there exists y such that AXY holds, and similarly for B as the set of x's such that there exists a z such that B holds, so then those two sets are disjoint. So it's enough to have C, which is some superset of A, which doesn't contain B. Okay, so such a C must always exist. And now the
C depends on y and z.
No. That's the important thing. So C doesn't depend on y and z. Okay, so, so it depends on A and B, but it doesn't depend on y and z. So one way how to define such a C is that you would define that C of X is true if and only if there exists y such that AXY holds. Okay. So that's one way how to define it, and this C will have this property. So such a C exists for trivial reasons, but now I want to ask, what can we say about the complexity of this C? So I will call this C as an interpolant of A and not B. And another subtle thing to notice is that if A is monotone in X, meaning that the variables in A, X in A, appear only positively, then you can actually fix C so that it is monotone in X. And now I would like to ask, what is the connection between the length of a proof of A or refutation of A and B and the interpolant C of A and not B? That's the general strategy of the interpolation technique. So I will show you again the Clique versus coloring formula, because I find this sometimes a little bit confusing what the interpolant actually does. But in the Clique versus coloring example, this is sort of clear what the interpolant should be. So we have the clique and the coloring again. So y is a clique in the graph represented by x. Z is a coloring in the graph represented by x. The following CNF is unsatisfiable. And the interpolant, what it does is the following. So if you have a graph which has is k plus 1 colorable, then the interpolant must accept the graph. If you have a graph which, did I say colorable or clique? If it is,
You said colorable, but
yes. If it is a k plus 1 clique, then the interpolant should accept it. If it is k colorable, the interpolant should reject it. So in this way, the interpolant distinguishes between graphs which are k plus 1 colorable and graphs which have k plus 1 clique and graphs which are k colorable. So it distinguishes the two. It accepts on the ones with clique and rejects on the ones which are colorable. And on the other graphs, it can do whatever you want. This is the only constraint that I know about the interpolant. Okay? It just distinguishes between the two alternatives. And here is the simplest form of the interpolation theorem, which is due to Clique, which shows that if A and B has a resolution refutation of size S, furthermore assume that A is monotone in X, then A and B have a monotone interpolant of monotone circuit size roughly S. So in other words, it tells you that if A and B has a short refutation, then there will be a small monotone interpolant between A and node B. So, I will not prove this, but I might give you a sketch. Well, so let's forget, the theorem is actually true even without the word monotone. So if A is not monotone in X, you still get an interpolant which will be just a circuit. The reason why Clique states it in the monotone form is, of course, that we can prove lower bounds for monotone circuits and we cannot prove lower bounds for general circuits. So that's why the word monotone is there. But if you want to prove it without the word monotone, then the proof is fairly straightforward. So you have your CNF AXY, BXZ, and basically the interpolant should tell you which of the two, if you fix an assignment for the variables x, so assume that you fix the assignment, then what you are getting is two CNFs which don't share common variables. Okay? So if you fix x, those two things don't share any variables, which means that at least one of them is unsatisfiable on its own. Okay? There is no connection between the two, so either this is unsatisfiable or this is unsatisfiable. And the interpolant is trying to tell you, given x, it's trying to decide whether this is unsatisfiable or this is unsatisfiable. That's what C does. Now, assume that you have a resolution refutation of this thing. So you fix an assignment for x, you feed it into this and into the resolution refutation. What will happen is that you are refuting two disjoint sets, two sets of clauses which have disjoint sets of variables. Now, it's easy to show that in a resolution refutation, that means that the refutation already contains a refutation of either this part or of this part. There is a little snack which I will not go into, it's a detail, but the point is that if you have a resolution refutation of two things with disjoint sets of variables, then at least one of those things will already, then the refutation will already contain a refutation of one of the two things. But everything I just told you can be done in polynomial time. So I will just take my assignment to the common variables x, feed it into my resolution refutation, massage the resolution refutation, and get out of it a refutation of either this or that, which gives me a polynomial size circuit which interpolates A and node B. So that's the sketch of the proof in the non-monotone case. In the monotone case, the proof is actually completely different and much simpler. And it shows that the circuit size is actually not O of S, but S. And it turns out that the structure of the circuit which interpolates the two is the same structure like the graph of the refutation. And what you just do is you just have your refutation, and depending on whether you are resolving on X or Y or Z, you just put there a little gadget into the refutation. That gives you a circuit, and that gives you an interpolant. Here's the clique and coloring again. And now I'm coming back again to the theorem of Rasborov. So if you fix a suitable K, then every monotone interpolant of clique and coloring requires a large circuit size. Now by the result of Krajicek, if you have a short resolution refutation, then you have a small interpolant which automatically gives you a lower bound on resolution refutations for this particular tautology. But given that I'm heading towards the end, so one point is that this corollary is exactly the same thing we had in the communication language, okay? But in the communication language, it was the same result, except that we said tree-like resolution refutation, okay? So this interpolation technique is, at least in this context, is exactly the same thing like the communication complexity, except you are getting better bounds. Better bounds meaning by proofs which are not only trees. And the way how to see this, this connection is that, remember this Alice and Bob game that you split the variables into two parts and they are supposed to agree on a falsified clause. So that game, after like suitably changing renaming the variables, is exactly the Kaczmar-Wigderson game for for a monotone function which, well, okay, it's actually exactly the Kaczmar-Wigderson game for the interpolant C. So the communication game we saw before between Alice and Bob corresponds to the Kaczmar-Wigderson game of the interpolant. And this way, the difference between the tree-like proofs and general proofs is similar like the difference between formula lower bounds and circuit lower bounds. So the communication complexity directly gives you lower bounds only on formula size, whereas which gives you lower bounds on tree-like proofs, whereas in interpolation you are talking about circuit size, and that allows you to talk about general non-tree-like proofs.
But here you're also doing monotone circuit size, which is
Yes,
simple.
yes. Well, so I will give this is roughly the end. I'll give just a little bit more remarks about the feasible interpolation. So the connection with the communication complexity was one. The second connection is that it also works for stronger systems than resolution. But then you sometimes have to make the computational model stronger. So, of course, you don't want to make the computational model so strong that you wouldn't be able to prove any lower bounds. But for cutting planes, the lower bound that I mentioned actually proceeds by interpolation. But it's not interpolation by monotone circuit, by monotone Boolean circuit, but it's an interpolation by monotone real circuit, which is an object which is a little bit stronger than monotone circuit, but it's not as strong as the general Boolean circuit, and one can still prove lower bounds on that, and thus one can obtain lower bounds on cutting planes. And there are similar other examples where you can apply feasible interpolation to other systems than resolution by first proving lower bounds for stronger computational models. Another thing is, and sometimes it happens that there are proof systems for which the only interpolation we know of is via general Boolean circuits. So those like degree D systems for degree 2 systems for cutting planes. So for certain systems, it's known that you have an interpolation for by Boolean circuits, which is nice, but you cannot prove lower bounds on Boolean circuits, so it doesn't give you an unconditional lower bound. For Frege system, for example, it's known that Frege doesn't even have interpolation by general Boolean circuits. Okay, so even if you prove modulo some assumptions, so even if you prove lower bounds for general Boolean circuits, it will not give you lower bounds for Frege. And finally, this clique versus coloring looks like something quite artificial because it requires the variables to be divided into 3 parts, x, y, x, z. The tautology has to have special forms. You want the variables x to appear only positively in one part, etc. But this is not essential at all. You can, by a little trick, you can transform any tautology whatsoever into a form which allows you to apply interpolation to it. So, for example, the bit pigeonhole principle that I mentioned before, one can prove a lower bound on the bit pigeonhole principle, which doesn't seem to be of this form at all, using interpolation. And that's it, except for open problems. So my first favorite open problem is Frege system polynomially bounded, but some more exciting question that we might actually prove is that what happens with bounded depth Frege system with parity gates. I told you before that bounded depth Frege, which is Frege when you work with bounded depth formulas, Aitai has proved a lower bound and it's a gem, but if you now add parity gates as one of the connectives and you use them in the proof, we no longer know how to prove lower bounds. Even though one can prove circuit lower bounds, bounded depth circuit lower bounds with parity gates. But nobody has managed so far to somehow use the lower bounds in circuit complexity and to get out of them lower bounds in proof complexity. So then one open problem, that's like I guess the most interesting open problem. Then the next one, which looks feasible, is to extend the lower bounds to degree 2 cutting planes. Degree 2 cutting planes are briefly defined, but we know lower bounds for tree-like versions of the system. It would be interesting to extend it to general DEG-like systems. And the problem related to this one is to design sort of randomized or multi-party version of feasible interpolation. This is motivated mainly by the analogy between communication protocols and computations. So in the case of resolution, it works nicely. So the communication in resolution corresponds exactly to computations. But if you take more complicated systems and more complicated communication models, there is no apparent connection between like some sort of computation and some sort of communication. So it would be nice to extend it to that one. Thank you.
Take a couple minutes for extra questions.
So I want to just maybe call into question whether open problem 2 is actually less exciting than open problem 1. Because open problem 2 actually you know, would be the gateway to proving size lower bounds for things like sum of squares proofs, which would actually be very exciting.
So I think problem 2 is more exciting.
But problem 1 is more, has been open longer, but actually I think maybe problem 2 would be more exciting.
So, question about problem 1. The usual way of proving lower bounds for AC at 0 with parity is this method of approximations, etc. If you relax your proof system to allow, low degree polynomials or some such thing, do we then know that sort of natural candidates actually start to have short proofs?
I would have to think about it. It's a good question. So I don't know from the top of my head.
Maybe what's a good candidate for lower bound here?
Like what is the thing that you expect is hard?
Yeah.
So like pigeonhole principle again.
Oh.
But to be kind of sure, so you wouldn't want to have like n plus, you would like the parities to be kind of the same. So if I say there is a bijection between n plus 1 plus n, this will have a short proof because the parities are different if I allow to use parity gates. But so if you avoid such trivial things, then pigeonhole principle from, let's say, n plus 2 to n should be hard.
Or, so in the mod 3, for example.
Or mod 3. So you can, yeah. When it comes to bounded depth frege, it's also open, or it has been open months ago, is that if you just have very simple system which is resolution, but instead of having variables inside the clauses, you will have parities. So you will have XORs of variables. So that's just, it's not even a bounded depth frege, it's just a conjunction, disjunction, and then parities. So for this is open to prove lower bounds, which is like the simplest thing that one might start with.
Other questions or comments? Okay, well, let's thank Pavel again.